Hi everyone. In preparation for the Calculus 1 course, we are still in the introductory topics. In this video, we will focus on special factoring forms. Some expressions present forms that can be factored without having to use any special techniques. We're going to call these special factoring forms. Essentially, these factoring forms will simply require that you recognize them in given situations. Of course, the previous video still applies, which means make sure that you look for simple factoring and/or grouping before you move on to trying to identify special factoring forms. The first form we'll discuss is called the difference of squares. The expression a squared minus b squared can always be factored into the product of a minus b with a plus b. If you wish to verify this identity is true, you can perform distribution on the right-hand side and convince yourself that you will get the left-hand side back. Here are some examples of how the difference of squares formula can be used. X squared minus 9 is clearly a difference of two squared terms. In fact, we could write x squared minus 9 as x squared minus 3 squared. You can associate x to the a that appears in the general formula and 3 to the b that appears in the general formula. And therefore we can write x squared minus 3 squared as x minus 3 times x plus 3. In the case of 9y squared minus 25, just make sure that you realize 9y squared is actually the squared value of 3y, and 25 is 5 squared. This time, 3y plays the role of a, and 5 plays the role of b. And therefore, we can factor 9y squared minus 25 into 3y minus 5. Those would be the a minus b terms, and 3y plus 5, the a plus b terms. Now, don't lose faith if you encounter something of the form like t squared minus 8. And don't panic either, despite the fact that 8 is not a nice squared value. You can, if you wish to, think of 8 as being the root of 8 squared, and therefore generate a difference of squares, where t plays the role of a, and root of 8 plays the role of b. T minus root 8 and t plus root 8 then become the factors of t squared minus 8. As you'll see in later sections of this introductory notions section, you can also rewrite root of 8 as 2 root 2, although it's not necessary. Similar to the difference of squares is the difference of cubes. A cubed minus b cubed can always be factored into a minus b, whose product applies to a squared plus ab plus b squared. Please note that a squared plus ab plus b squared will not be factorable anymore. So you need not spend any energy trying to factor a squared plus ab plus b squared later on. For example, x cubed minus 64 can be thought of as a difference of cubes because 64 is the cubed value of 4. With x playing the role of a and 4 playing the role of b, x cubed minus 4 cubed becomes x minus 4, x squared. 4x is the product of a with b, and 4 squared is the b squared term, so 16. 1000t cubed minus 27 is also a difference of cubes, as long as you recognize that 1000t cubed is actually 10t all cubed, and 27 is 3 cubed. This time 10t plays the role of a, and 3 plays the role of b. 10t minus 3 is then a minus b, A squared means squaring 10t, and that will produce 100t squared. The other terms, AB, are 10t times 3, and 3 squared is 9. Sums of cubes are very similar, aside from how the signs are presented. A cubed plus b cubed can be decomposed or factored into a plus b times a squared minus ab plus b squared. So notice how, in contrast to the difference of cubes, the signs are just distributed differently. X cubed plus 125 is a good example of a sum of cubes, as 125 is 5 to the power 3. With x playing the role of a and 5 playing the role of b, we can then apply the sum of cubes formula. These different rules can be applied to higher powers in certain situations. Difference of natural powers, so by natural powers I mean positive integers, a to the n minus b to the n. Now this is really a generalization of the difference of squares and the difference of cubes formulas that we saw earlier. We don't expect you will all remember this formula by heart from the onset, but if you do apply it a few times, you will recognize how the pattern develops. So in the case of the difference of powers, of common powers of a and b, so a to the n minus b to the n, a minus b will be a factor, and it will leave behind that bigger term that you see on your screen. Now, what would be great for you to recognize is to notice how the powers of a decrease at every term. So we have a to the n minus 1, followed by a to the n minus 2, followed by a to the n minus 3, and in the last term there is no a that appears whatsoever. Whereas in the case of b, the powers of b increase, starting with no b's at all in the first term, and then b squared, and eventually b to the n minus 1 in the last term. For example, x to the 5 minus 32 is the difference of x to the 5 minus 2 to the 5. So this is clearly the difference of two natural powers. X and 2 both have 5 as their common exponent. Therefore, we would expect x minus 2 to be a factor. And in the remaining term, notice how we are adding expressions that all have x's and 2's, but in powers that vary. In the first term, x to the 4, 3, 2, 1, and finally in the last term, no x's at all. And 2 has increasing powers, no 2's in the first term, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. And here would be a factored version of x to the 5 minus 32. In this last example, we're going to try to factor the expression 5x to the 7 minus 405 times x cubed. Now remember a warning that was issued a little bit earlier in this video. Always look for simple factoring or grouping before you move on to factoring forms that are recognizable. You'll notice that in this example, both 5 and 405 have 5 as a common factor, and x to the 7 and x to the 3 share x to the power 3, and 5x cubed can therefore be factored, leaving x to the 4 minus 81. X to the 4 minus 81 is the difference of x to the 4 and 3 to the 4. So some of you will identify this as being the difference of a common natural power to x and 3. And if you do that, you will then have a factored form that pulls out an x minus 3 and x cubed plus 3x squared plus 9x plus 27. Now remember that when you have 4 terms, there is a possibility that grouping might actually be applicable. In this case, turns out that it works very neatly. The first pair of terms, x cubed plus 3x squared, have an x squared in common. The last pair of terms, 9x plus 27, have 9 in common. And that generates an x plus 3 that is shared by both of these pairs. X plus 3 can then be factored, leaving x squared plus 9. Here's a different approach with the exact same expression. Once again, simple factoring is probably the best way to start this whole problem. And then although we see x to the 4 minus 81 as potentially being 2 terms of the power 4, some will think of it as a difference of squares. In fact, x to the power 4 is x squared squared, and 81 is 9 squared. Differences of squares, where x squared plays the role of a and 9 plays the role of b, can be applied here. And therefore, 5x cubed now becomes a product of, or a factor of, x squared minus 9 times x squared plus 9. That middle term, x squared minus 9, this time is clearly a difference of squares, where x plays the role of a and 3 plays the role of b. X minus 3, x plus 3 would be its factored version. X squared plus 9 is a sum of squares that does not have any factorable forms.